Hello students, now we are going to find out the solution of linear congruence 15x congruent to 25 mod 35, and how to find the solution of this type of linear congruence. The theory part I've already discussed in that theorem. We know that in that first part of the theorem is that like this: ax congruent to b mod m has a solution if and if g divides b, where g stands for the GCD of a and m, and if the solution exists, there will be exactly a g number of solution. So here we have, according to the question, 15x congruent to 25 mod 35. We have to find whether the solution exists or not. First, we have to find whether the solution exists or not. If it exists, what are those solutions? So here, 15x congruent to 25 mod 35 is of the form ax congruent to b mod 5. By comparing it with this, we have a is equal to 15, b is equal to 25, and m is equal to 35. And we know from that ax congruent, from that theorem, ax congruent to b mod m has a solution if and only if g divides b, where g here stands for the GCD of a and m. So now here, what will be g according to the question? According to the question, g here is equal to GCD of a and m, which is equal to GCD of 15 and 35. So the greatest common divisor among these two integers, 15 and 35, is 5. And let's see whether 5 divides b or not. Now, g divides b, that is 5 divides 25, because if you divide 25 by 5, the remainder gives you 0. So by definition of divisibility, we say that 5 divides 25. So there will be exactly g number of solutions. So therefore, according to question, we have g is called, therefore a 15x congruent to 25 mod 35 has 5 solutions, since g divides b, that is 5 divides 25. Next step, we have to find what are those solutions. So to find those 5 solutions, what we need to do is we divide am equal to 35 by a is equal to, so you have to divide this 35 now by 15, by a is equal to 15. And when you divide it by division algorithm theorem, by division algorithm, which is in unit 1, algorithm theorem, there exists unique quotient and unique quotient q and r. Unique q here equal to, so what will be the quotient here? It will be 2, and remainder r is equal to 5, such that this 35, when you divide it by 15 into the nearest one to 35, when you divide it by 15, it is 2, that is 30. So the remainder gives you 5. So here we divide m equal to 35 by a is equal to 15. So by division algorithm, there exists unique integer q and r, such that 35 can be expressed, because if you have a and m belong to set, the statement of division algorithm, with m different from 0, then there exists unique integers q and r, such that a can be expressed when you divide a by m into q plus r, where r here is greater than or equal to 0, but strictly less than less or equal to m minus 1. So we are following this using this theorem, that is division algorithm theorem. When you divide m equal to 35 by 15, what we get, the quotient is equal to 2 and remainder is equal to 5, such that is equal to this one. Next, applying, since till you get remainder 0, so applying Euclidean algorithm, again these are in unit 1, algorithm theorem. Continue now. Next step is you divide this a, divide A equal to 15 by the remainder 5 by R is equal to 5 till you get the remainder to be 0. So when you divide A is equal to 15 by R is equal to 5, what we get is, again there exists unique integer cube. Say cube 1 now, I'll denote the quotient so that it will be differentiate from this quotient cube equal to 2 and R1 here. So here in this case, when you divide A by 5, so 5 3s gives you 15. So there exists a unique quotient 3, cube is equal to 3 plus the remainder R1 here is equal to 0. So here cube 1 is equal to 3 and R1 is equal to 0. This we proceed. Here you have got the remainders to be 0. Now in case if the remainder is non-zero, you continue to divide that quotient, that divisor, by the remainder till you get the quotient, till you get the remainder to be equal to 0. So here there are only 2 steps required to divide. First you divide A is equal to 35, M is equal to 35 by A. Next step, if the remainder is non-zero, you divide that A here, that is 15, by the remainder 5. Continue in that way till you get the remainder to be 0. But here in this question, 2 steps only are required, because in the second step, the remainder will become 0 itself. So we'll stop here for this part. Now we know from one of the properties of GCD, we know that if G is equal to GCD of A and M, then there exists R and S belong to set such that G can be expressed as AR plus MS. So using the above properties, what do we get is, what is GCD of A and M here? G here, if you compare with this question, G is equal to 5, and what is A here? It is 15 and M is 35. So from here, there exists by applying this 5 now can be expressed as a linear combination of this one. So there exists R and S such that 5, that is G here, can be expressed as 15 into R plus 35 into S. So in this case, in order that the sum of these two with the linear in order to get 5 here with the linear combination of 15 and 35, what shall we put here? Here you have to put minus 2, the nearest, such that will become minus 30, and here S you put it by 1, such that 15 into minus 2 gives you 30 plus 35 into 1 gives you 35, which gives you the difference of these two gives you 5. This R and S, they are integers, they can be positive or negative. So, or you can write this one. So from here you take this one, let U naught is equal to minus 2, or let me write here, let R is equal to minus 2. So this implies that 15, from this step you can bring this to the right hand side, you can write it as 15 into minus 2 plus 35 into 1 gives you 5. Now multiply this both sides by 25, that is multiplying both sides by 15 by 20 by B is equal to 25. So what do we get is 15 into minus 2 into 25 plus 35 into 1 into 25 is equal to 5 into 25. Next, you divide both sides by G equal to 5. What do we get is 15 into minus 2 by 5 plus 25 plus 35 here. into 1 into 25 by 5 is equal to, when you divide by 5, so the right hand side become 25 only. So this implies that 15 into minus 2 into 25 by 5 is equal to, bring this to this side, so we have 25 here minus 35 into 1 into 25 by 5, or you can write it as 15 into minus 2 into 25 by 5, okay, is equal to 25. I want to write plus here, so for that I have to write 35 into minus 21 into this gives you 25 divided by 5. So in using the definition of concurrences, if A is equal to m cubed plus r, this implies that A is concurrent to r mod m. So treat this m here as, this m is 35 cubed as minus 25 by 5 here. Okay, this one. We know that if A is equal to m cubed plus r, then this implies that A is concurrent to r mod m. So treat this 25 as m cubed as minus 25 by 5 and r here as 25. So this implies that 15 into minus 2 into 25 by 5 is concurrent to 25 mod m. Okay, by comparing it with this. So when it is concurrent to 5, so that is, what is the equation? We have 15x is concurrent to b mod m. So that is mod 35, sorry, here m is 35. So this implies that x here is equal to, or x here is equal to minus 25, and 5 here gives you 5 only when you divide, so it gives you minus 10 mod, x is concurrent to minus 10 mod 35 is the solution. Or you can write here x is equal to minus 10 plus t into 35 by 5 is the solution. Sorry, this is mod 35 by 5, or 35 by 5 is the solution. You refer to that theorem. So from here, by taking t here, because there are 5 solutions, so take t here is called 0, 1, 2, 3, 4, 3 and 4. So by taking t equals 0, you'll get one solution. By taking t is equal to 1, you'll get another solution. Similarly, by taking the rest, t is equal to 2, 3 and 4. So therefore, replacing t by this 5 value, you will get the 5 solution of the linear concurrence 15x concurrent to 25 mod 35, this one. Okay, I think it is clear to you. If anything is not clear, we can discuss it again. Okay, so I'll stop here for today's